We worked with our partners Intel as part of their data center builders program, which is a program where Intel, gives companies like ours access to new servers, develop the technology, build on Intel stuff. We started from kind of an observation. How many of you have seen this? You have?
Yeah.
Okay. Do you have any comments on it before we move on?
The fact that it's upending all storage systems and the way we look at storage.
Yeah. Right. Okay. So this is how that setup looks like. So we started with this, and we thought we can't leave this like this, and hold my beer. Let's see what we can do. And this is how that setup looks like. So it has 12 nodes with two CPUs, that much memory, and 1.5 terabytes of Optane persistent memory NVDIMMs on each node, 32 terabytes of NVMEs in each node, and a Mellanox ConnectX 4 NIC. And they're saying they use RDMA, right? And I guess the implication is we use RDMA, therefore it's fast, right? Which, and the most damning part about that test is that they say that for the best performance, every VM runs on the server node that owns the volume where the HDX file is. Which means, it's hyper-converged, therefore we can allow ourselves to have one of the copies local, and we'll perform all the reads and writes to that. At
least the reads, anyway. Yeah.
At least the reads. And because of the way that setup is done, and because of the size of the active set, that all gets cached in the Optane memory, and it's actually reads from persistent memory.
I think it's called cheating, isn't it, really?
All right, so how many of you are familiar with the concept of handicaps in chess or golf, right? So we thought it would be, bad form to do it like them. So we went and did this. So first, it's not storage spaces direct and Hyper-V. It's StorPool with KVM and Linux, right? Secondly, we don't need these. Third, we don't need RDMA. So we replaced that NIC with an Intel NIC. And most importantly, it's not a local copy. It's a 100% remote, right? And how the setup looks like, you have 12 nodes with 2 times 25 gig on each. To a single switch, we're not looking for redundancy. If you have 2 switches, it will work the same way. There is no difference really. This is our resource utilization. So out of each server, we have 4 NVMe drives in each server with 8 StorPool server instances running on 4 CPU cores, 4 StorPool block instances running on 2 CPU cores. So the total CPU usage of StorPool is 6 cores so far, right? And we have a bunch, in this case, 8 virtual machines to run the workload. You might notice the StorPool uses 6 CPU cores just to run the guest kernels and the FIO workload in there. That's 4 times 4. 16 threads or 8 CPU cores, which is more than the whole storage system. When we run this at full load, meaning we saturate the storage system, it ends up using about 14 CPU cores. Now, 14 CPU cores, well, 1 point, it's 6 for StorPool and 8 for the virtual machines, right? It's not 14 for StorPool, okay? 6 for StorPool. 14 cores total, 6 of which StorPool, 6 cores in a kind of cost and density optimized hypervisor. 6 cores represents about 15% of all the CPU cores in that server. So the whole server has 40, and we take not 4, but 6. In terms of results, we got 13.8 million IOPS for reads. And this is reads inside the virtual machines. Right. So there is 96 virtual machines in total, and we run FIO in all of them. Right? So the Microsoft record is down. We can do better, and we can do better without a lot of the
Constraints that they've imposed.
very expensive hardware and without cheating, right?
Yeah, because you're showing random reads, and if
They
you're
also
using
are.
huge amounts of cache, then you're just reading out of cache.
Yeah.
And it's just moving stuff
Yes.
out of cache.
Yes.
So what Microsoft are showing is,
Yeah.
I could use a word for it. I won't use a word for it because polite recording. But something like BS, when you see massive random reads, it's ridiculous.
Yeah.
Now, obviously, you've cut it down, which shows the ridiculousness of what Microsoft are doing, because you can do it with.
We can do it
so fewer
without the cache.
resources.
Yeah.
Yeah.
So, in fact, in this this setup, we actually don't do any caching in RAM. So every single of these operations comes from an actual NVMe drive underneath. When we use RAM, so there was, I think something I skipped was 25 gigabytes per node we use for metadata, right? Which
64 gigabytes per second sequential read?
yeah, want to see that?
Live demo.
Live demo. So it's
Across
not
12 nodes, 25 gig each? I mean, it's like
yeah, it's a
I
lot.
think they're twin.
not even a terabyte or cache, right?
No caching. It's not exactly sequential. So it's 96 VMs, each doing a
I
sequential stream.
understand.
Yeah,
I understand. 64 gigs is
6 gigabytes per node. Well, 5 gigabytes per second per node, which is the
still.
Close to the theoretical
Very good.
limit of what you can push across those.
across this network, right? Let's try that. Okay, let me see where I have that. Right, so this is a different dashboard from the same kind of metrics database. I did specifically for this demo. This actually collects from the virtual machines themselves. So I have 12 nodes, each with eight virtual machines. When it counts a VM here, it means we're receiving metrics from it. So sometimes, total IOPS, what is that? That is, do you guys see, or should I try and make this bigger? Try and make it bigger. It's the sum of reads and, for all servers, and writes, the sum of write operations for every server. Go back, and I have requests in flight, which is the sum of average queue size in IO start in all virtual machines, right? Switch ports, because you asked, is 64 gigabytes per second even possible, right? So we'll see how much of the 600 gigabit total. What is 600 gigabit total? It's 50 gigabit per machine. When it's 12 servers, it's 600 gigabit total bandwidth between machines. And we get the guest average wait time, which is extremely noisy at the moment. One reason it's noisy is that the source data where we get these statistics from are quantized. So that counter is only incremented if it accumulates a millisecond of wait time. When you have many operations per second, that's not a problem. But when you have just one or two, that becomes a waterfall like this. And hello. Let me just get this to work.
And it's 70 microsecond response time without NVMe over Fabric?
Yeah. So
70 microsecond.
correct. Yeah. Do you want to see that first, or the
No,
60
go ahead.
gigabytes
I'm
per
sorry.
second
I'm just still trying to process this
Yeah.
performance.
So
He's doing math.
yeah.
Go ahead.
Let me just try and get connected here. So for some reason, my VPN to Sofia is getting disconnected. Well, this lab is somewhere here on the west coast of the US, but I'm still going back to Sofia and then back. because of security. We have it set up there, and we don't want to
And,
have access to everything everywhere.
Write latency is measured from the host to the storage server and back again, right? This is the acknowledgement of the write operation at the host takes 70 microseconds on average.
I'm going to correct you there. It's 70 inside the virtual machine.
At the virtual machine level, even
Yeah,
better.
so it's,
okay.
we're
So it's not,
looking
you
at-
get virtual machine stack, and then you've got the device stack, and then you've got, okay,
Yeah.
70 microseconds.
Maybe
And-
make the font a little bigger.
Yeah, sorry about that.
Whoa.
So there's the Intel Lab. No, Intel Lab tester, yeah. Tester is this machine, let's get to it, is just a VM we have in there that we can run these tests from, right? Yeah, and I'll make the font a bit bigger, I guess.
What's your read latency? If your write latency is 70 microseconds,
It's actually more, which is
like
annoying.
85 or something like that?
All right, so one by one.
That's all right, I'm sorry.
So this is, well, it says field here, but it's the wrong name. So it's a random sequential read with QDEP 16, block size 228. It's nothing extraordinary. We're going to run this in parallel on the 86 virtual machines. So VMs all is just the IP addresses of the 96 VMs, and we're going to do read, hit enter, make that slightly bigger. This is 65 gigabytes per second at the moment from fully allocated volumes, right? All remote, all going over the network, including the virtualization stack, including everything. And the metric should come in, well, I've disabled the refresh stuff. The metric should come in any moment now. So that's total queue size, 1,500 IOs outstanding. It's 96 VMs times number of IOs. Number of IOs per second, 500,000 times that. Average latency, about 3 milliseconds. A lot of this is queuing, so I can probably reduce that queue depth and I'll get the same result and I'll get lower latency. It's a fully saturated system. And this takes at least 2 kind of 20-second cycles to get up to there. The reason for that is I wanted to have the metrics from the switch itself, right? And that switch updates its counters every 20 seconds. So, we need to wait for it another cycle, another 20-second cycle to see the numbers. Right, so 570 out of 600 gigabit per second available on the network, which is like 95% network utilization. Right. All right, so if we wanted to do everyone's favorite benchmark, the random reads, Chris, that's your favorite benchmark?
Yeah, absolutely. So useful.
All right, so this is random reads 4K QDEP 64 going, and at the moment that's 13.1, and when you're and went up to 19. The reason it went up is not data caching; it's metadata caching. So because we warmed up the metadata, so it's 19.8, 19.9, and there they are. So these are collected from 2 different places. This is what FIO reports inside the VMs. This is what the guest kernel reports in IOStat, right? It's 13.8 million IOs per second. Total queue size of 5,000 and plus. And And when you do 5,100 divided by 96 VMs, you get 53 IOPS per second. We actually asked for 64, but FIO is not fast enough, so it can't push the IOPS to the guest kernel, right? And while doing this, while doing 3.8 million IOPS per second, we have 400, that may be too small, 400 microseconds. Let me try and fit them all on one screen without resizing. So you get 400 microseconds latency at this moment in time, and that corresponds to 3.8 million IOPS per second.
Refresh my memory, that's how many backend nodes?
53?
How many?
How many backends?
Same as Microsoft, isn't it? 12, didn't you say?
Same
12?
servers.
Same servers?
12
And how
with
many?
12
nodes?
How many?
12 servers?
12
Backend?
storage nodes.
Yeah, 12 storage
with
nodes.
4 NVMe drives each, so that's 48 NVMe drives. Right.
Some pretty sweet numbers.
Yeah. So the main reason I'm showing you the read side is it was kind of the headline number of the Microsoft report, right?
Yeah.
Right, so moving on to latency. If we, instead of kind of pushing the system to its limit and saturating the network to, what is it, 80 plus, or 85%, if we ask for fewer IOPS per second, on this one, where is it? This one. So if we ask for fewer IOPS per second, I think I have a limited with 50,000 IOPS per VM. That's 4.8 million IOPS per second random read total. I'll give this a few seconds to get the metrics in. Let's see. So it says.
It was good numbers even when it was under load, so this is.
Right. So 4.8 million IOPS per second. This queue depth here of 400 something, that's
Divided by the 96.
divided by 96 VMs. I was thinking if I should show that like queue depth per VM or total queue depth. I think it's fairer to have it as total queue depth. Although we've asked FIO to do 64 because it's rate limited, it will do fewer, right? And the latency you get is 140 microseconds, right? While doing 5 million IOPS.
And it's random read?
Random reads, full width. I have the I have the active set thing. So the StorPool KVM setup has 96 VMs, 500 gigabytes each, which is 45 terabytes of data. It can't fit in memory. It doesn't have the obtained per system stuff. It's all 100% reads from the NVMe drives underneath. And it's about 40% of the system capacity.
Yeah.
So,
Amazing.
I'm guessing like what goes through your mind is, how are these guys cheating, right?
So that's your protocol that is, because you're not running TCP/IP over that part, you're running your own protocol.
Yeah, that's our protocol. It's actually, it used to be our protocol in raw Ethernet frames. However, we've moved to our protocol in UDP packets. So now it has an IP header and a UDP packet.
Right.
But that doesn't make any difference to performance. The only reason we did that is compatibility with routed networks. So in larger data centers, you would have these routed.
Yeah, because okay. The UDP still makes sense because you don't have to wait for everything to do a round trip
Yeah, yeah.
every pack,
So
every
it's
block.
still in terms of how we process it, it's still processed the same way. It's a packet comes through the network. Is it for us or not for us? And
Read it scan. Yeah.
we can use RDMA, right? And RDMA makes sense. So if you have a Mellanox NIC, like getting that queue and doing RDMA is actually
Probably the most efficient.
quite more convenient than doing the Intel and others with the SRIOV and VFs approach. That's a lot more complex, right? But we don't need it to get this kind of performance, right?
Does your protocol have a name?
It's the StorPool protocol, right?
It's very creative.
It is also, the product is also like that. So it's
Okay.
StorPool the company and StorPool,
Right. Okay. Cool.
The product, the protocol,
everything.
Easy messaging.
might be able to remember it.
Okay. We wanted to see, this was latency under random reads. I can do, where is this? Latency under kind of limited writes. Hello? No, limited reads and writes. Limited 10K per VM, which does, for how many? Why doesn't it? Oh, come on. Yeah, works now. So here they are. It's not many. It's like a million IOPS per second, including writes. And you get reads at about 200 at the moment and writes at about 100. For writes, so this is on StorPool's next release. It's called version 19. Right? It's like web browsers.
So you're doing a mixed workload, 50-50 read-write,
70-30
70-30
Read-write.
read-write,
4 kilobyte large queue depth.
and 1 million IOPS roughly, and you're getting 200 microsecond read and 100 and
Yeah.
so of
Right.
write
Yeah.
latency
Measured inside virtual machine.
at the virtual machine
Yeah,
level.
yeah. And going back to why we're doing this, like we want virtual disks which are as fast as local SSD, right? You want that because if you have a database, if you put it in a VM, you want it to work.
No, I understand that. It's just I don't believe I don't understand the numbers. I understand the numbers, but I don't.
You think they're too low then, right? You think they're too?
No, they're very good.
No, I mean too low in the sense that you think they're lower than you would have expected.
They're much lower than I expected from a response time. They're much higher than I expected from number of IOPS and number of gigabytes per second. Your standard enterprise class $1 million storage system is not able to do this.
No, but it has all the encumbrances of being a shared
Standard
environment.
software defined version of these sorts of systems with tiers of SSDs aren't able to do these numbers.
Well, this is where marketing defined comes. Like this is the difference between a real technology and.
You're talking NVMe over fabric types of response time.
Yeah.
Only we're talking 1 million IOPS at a whack, and we're talking we're not talking read 100% read. We're talking mixed
Yeah.
read-write workload.
It can do, I think it can do about 5 million.
You guys
bits.
really need some better marketing, I'm thinking.
Yeah. I think Boyan has something to say about that.
we can show a couple of case studies that.
Yeah. So
nail the point.
what we have left is a couple of case studies, and then a short, we're hoping, off camera.
Let me see. 70-30.
Yeah. What was I? Yes, I remembered. This is, just one of the VMs, some VM.
You're making the CPU work.
You guys should have started here and worked your way into the architecture later.
I think. Yes, we want to do that. Okay. So this is where the statistics in the bug come from. This is just one of the VMs. And that VM is doing 7,000 plus 3,000 tiles per second.
And 70-30.
Yeah.
Yeah, I don't think it's a question of saying they're not real. It's just,
Oh, no,
I just was curious to see
where the source was.
what Ray was.
Write weight
Thinking or
and
expecting.
read weight, 200, 100.
Yeah, that lines up perfectly.
So one more thing on the Microsoft test. Another thing they did is they reported a latency number, which was 40 microseconds. That latency number doesn't align with their other numbers. So there is kind of a...
But the maths doesn't add up.
Doesn't, no.
Yeah.
So there is, like Ohm's law, current and voltage and resistance, these three numbers align. So IOPS and request in flight and latency. Right, so
Do you think that's because they were serving the majority of stuff out of
Out of the Optane.
out of the RAM and
so
Optane?
I think what happened is it wasn't very well described. So I think they measured latency in the host, and the benchmark is running in VMs. So most of the latency
Oh, right,
was
okay.
virtualization overhead, not the storage itself.
So they were taking it from the actual Hyper-V host, not the
Yeah,
test.
yeah.